All right, thank you for coming back, and thank you for being here. This is our second panel. We're going to talk about major scientific results. This morning we have a panel of 3 speakers. Our first speaker will be Avner Vengash, who you heard from in the introduction. Avner is a professor of geochemistry and water quality here at Duke. Among many topics, he's worked on naturally occurring contaminants such as arsenic, fluoride, and boron in groundwater around the world, here in North Carolina, the Middle East, and many other regions. He also researches the environmental effects of mountaintop mining and shale gas extraction, the topic of our symposium today. And the title of his talk is Methane and Water Contamination Associated with Shale Gas Development and Hydraulic Fracturing. I'll go ahead and introduce all 3 people at first. Our second speaker in the panel will be Bob Howarth. Bob is the Atkinson Professor of Ecology and Environmental Biology at Cornell University. He's well known for his work on the fate of nitrogen in the environment, including dead zones, such as what occurs in the Gulf Coast each summer, and for international research on biofuel production. One of his current interests, however, is climate change and the net greenhouse gas balance of shale gas production and use. And he'll talk about the greenhouse gas footprint of shale gas. Unfortunately, our third speaker, Art Berman, from Labyrinth Consulting Service, Art spent 20 years with Amoco, is stuck. He's trying to get here from Anchorage, and he's not sure what time he's going to get here, so we've lost him for the morning, at least. Our fourth speaker will be Kelvin Gregory, Assistant Professor of Civil and Environmental Engineering at Carnegie Mellon University. He works on such issues as the fate, transport, and toxicity of nanomaterials, another emerging issue, and on the management of produced water from unconventional oil and natural gas development, the topic of his talk today. And his title is Navigating Water Management Challenges During Hydraulic Fracturing for Shale Gas Production. So we'll begin this session with Avner Vengash. We'll run the same drill we did before. There'll be students walking up and down the aisles to bring you questions. And if you have any questions, just jot them down onto the note cards and they'll bring them up to the front. Okay, Avner.
Thank you, Rob. Let me acknowledge my co-authors in this study, Rob Jackson, Nat Warner, Stefan Osborne, and Adrian Down. They're all somewhere here. And we all, this is a study that has been conducted at Duke for the last 2 years almost. As you heard, shale gas development is a wide-scale phenomena in the United States, and basically many basins, and you can see it in the map, are being explored right now for unconventional shale gas by this process of hydraulic fracturing. In this process, thousands of wells have been drilled, and one of the examples is the Appalachian Basin that you can see in the map here. And since the boom basically started at about 2008, where thousands of wells were drilled and fracked to explode shale gas. And just to give you an example, in Pennsylvania, there were only in 2010, about almost 1,400 wells were drilled and fracked just in 2010, the same number, even more, 2011. And the question that I would like to address in this talk, there are 3 questions that I would like to address, and again, the important thing would be the question mark, because I don't think we have, or nobody has a real answer. So the first question, I would say, do we have enough water? The second question, does shale gas drilling and hydraulic fracturing cause contamination of water resources, specifically drinking water? And the third question, does produced water cause long-term ecological effects and health risk upon disposal of flowback and produced water that coming together with the gas that is produced from wells? Those are questions that maybe are going to touch in this talk, part of our study. Again, do not expect to have answers, maybe some more questions. So basically, when we talk about drilling and hydrological fracturing, we talk about a large amount of water. For example, we talk for hydraulic fracturing, estimate between 2 and 4 million gallons per well. So if you do a very simple calculation, those 1,400 wells per year that were drilled and fracked, you give up to a very simple number of about 5,400 million gallons per year. And if you divide it, just for the argument, for day, you get 15 million gallons per day. Well, if you're living here in Durham, you use 25 million gallons per day. So this is the same amount of kind of a small city, like in Durham, North Carolina, would consume every day for its survival. And the answer then, is this a lot of water? Depends where you live. In northeastern Pennsylvania, I would say it's not a critical issue. But if you're living in Texas and you are under a drought, severe drought ever in the last 100 years, that amount of water is extremely precious, and therefore the amount of water is a limiting factor for fracking and for hydrological fracturing. So the question of water availability is something that we put on the table and probably will become a major issue. Specifically, if we talk about climate change, major trends of decrease of water availability in the Southwest, and how this would affect different shale basins in those areas. The second question, does gas drilling and hydraulic fracturing cause contamination of drinking water wells? And this is diagrams made by Scientific American. You can see, if it works, doesn't. You can see the large volume of rock between the target formation and the shallow aquifer. And the question is it possible that fluids and gas can move from the target formation that's being fracked into the shallow groundwater formation? And in Duke, this is the study that we conducted, focused on northeastern Pennsylvania and New York. We published the study last May in the Proceeding of National Academy of Science. And the result of the study showed that if you are having a private well and you're living next to a shale gas production well, less than 1 kilometer, you have high probability of having high methane in your well. We showed that, and this data now being reinforced with more, about 200 wells that we collected since the conducting and publication of this study. And we showed that natural gas occurs in wells in Pennsylvania. However, if you're living next to a producing well and frac well, you have much higher probability to get a lot of that. And it's not only the high methane in the well, we also using the isotopes of methane, both the carbon isotopes and the hydrogen isotope as fingerprint to ask the methane where it's coming from. And we use this to try to delineate the sources of the methane in the wells. And our results show that those high methane wells located near the shale gas well have very distinguished isotopic fingerprint, which is very similar to the Marcellus methane, whereas well located away from those wells have a totally different isotopic fingerprint, which is more mixed biogenic, thermogenic. The thermogenic methane is the methane that is being generated and produced by a production well. So this distinction enables us to determine that indeed deep methane, deep stray gas is actually coming to the well. In contrast, we didn't find any water contamination in those wells. So the chemistry of the wells, and we have a large spectrum of geochemical and isotopic fingerprint showing that wells located near shale gas well with high methane, they don't have any chemical contamination. So this kind of a conflict result we have here. And basically what we envision that one of the processes that could cause this migration of the deep stray gas from the formation would be through the actual fracked well themselves, through improper casing and leak of high pressurized wells into the natural fracture system would cause migrations of gas from the well into the groundwater system, which find themselves as a free gas into shallow wells. And if the shallow well is located next to this frac well, it will have higher probability to be exposed to this stray gas well that's coming from depth. This is one option, one most likely mechanism of methane contamination of the well. There may be some other processes. In a study that we are conducting right now and in a paper that was just submitted, we're actually finding another phenomena. We're finding that many of the shallow groundwater having high salinity. And the geochemical fingerprint of those saline water are very similar to the Marcellus brine. So for us, we have a very important evidence for migration and connectivity between the deep brine and the shallow aquifer. However, we see that this connectivity has nothing to do with the current drilling and fracking activities. It's a natural occurring phenomena. It could be either through a natural fracking system, or it could be through hundreds of thousands of wells that have been drilled and abandoned in the area and can be the connected way between the deep formation and the shallow formation. So in short, we do have evidence for stray gas contamination of shallow private wells located less than a kilometer from gas well. We do not have evidence for chemical contamination of the water associated with those wells. The third question I would like to address would be, does produced water disposal cause long-term ecological effect and health risk? So what is in produced water? They're very saline. It's about 10 times the salinity of seawater. They contain high bromide. It's a natural occurring bromide that due because of the nature of origin of those brine from evaporated seawater in the past. And high bromide in water, it's a bad news because the bromide, even if you dilute it to a very low concentration, once this water being transported and being used for domestic application, you can generate very highly carcinogenic disinfection byproduct like trihalomethane upon chlorination of this downstream water, which is enriched with bromide. So having bromide in the water is a major issue. The produced water has high level of toxic element like barium and arsenic, and it has very high concentration of natural occurring radioactivity like radium, which is highly carcinogenic. In our lab, we measured level of up to 5,000 picocurie per liter as a radioactivity measure relative to drinking water standard, which is about 5. So that's kind of the danger of produced water. What we do with produced water, there are several things that we can do. We can inject for underground through deep disposal well. We can discharge to a nearby surface water body. We can move it to municipal wastewater treatment plant, to commercial treatment, industrial wastewater treatment plant, or from an environmental point of view, of course, reuse for future fracking with or without treatment. Now, this will be, of course, the better practice to use. However, because of this high salinity and chemistry, there's a limit how much you can reuse this produced water. So what does it mean, a deep injection? Let's take Ohio, for example. In Ohio, there were about 140 million gallons were injected only in 2009. In 2011, a lot of the produced water was shifted from Pennsylvania to Ohio, and it was increased by 50% because Pennsylvania banned shipment of drilling wastewater to sewage treatment plant, as it been done before. And as a result, the injection well in Ohio is being worked very intensively, but then you heard about the earthquake. Now, we're not going to talk about that, but a series of earthquakes associated with deep well injection of the produced water. As mentioned before, it's not the fracking activity, but rather the injection of produced water may cause or trigger this earthquake that was found in Oklahoma, Arkansas, and in Youngstown, Ohio. Just in the New Year Eve, they have a 4 Richter earthquake that may be associated with that. So if we cannot inject back to the deep well injection, it has to go back to the streams. And if it goes back to the stream, as a study done by a Duke student, Nat Warner and Sidney Christie, here in the pictures, they were looking at the different sites in western Pennsylvania to see what actually takes place on the ground when you dispose those brine into the surface water. And what they found is that you have an area of about 500 meters downstream from the disposal. Here you can see the chloride concentration versus distance from the discharge site. And you can see that the water at that area would have high concentration of chloride, bromide, barium, and other trace elements that associate. So we forming kind of ecological hazard in this area. But even more severe, we found if we're looking at the radium concentration at the sediments in that area, we see that much of the radium from the produced water has been absorbed into the sediments of the river, and we are creating in sediments high level of radioactivity, which will be absorbed and bioaccumulate in the ecological system. So one of the recommendations, if you're doing fishing, don't eat the fish coming from this area. So what are the take-home messages from my talk? Shale gas exploitation and hydraulic fracturing may save United States from foreign oil, but seems to cause some methane contamination in shallow drinking water wells in the Appalachian Basin. It's important to emphasize that our studies has its limit. It's maybe true for the Appalachian Basin in northeastern Pennsylvania. It may not be true for other basins which have different types of geology, less fracture, less connection between the shallow and the deep aquifer, so it's important to emphasize that. We also, the take-home message, that disposal of produced water from shale gas well poses significant risk in waterways in Pennsylvania or elsewhere where you're going to dispose it. And I think the most important message that our study we are trying to emphasize is that sustainable and long-term shale gas development will need to accommodate the environmental issues associated with shale gas drilling and hydrological fracking. And that is the essence to enable the future of these so important resources in the United States. Thank you.
Abner, do you have the pointer? Do you have the pointer? Yeah, there's. Oh no, the other one. That's the one I gave. Okay, this one works here. Okay, as before, the students are coming around with the cards. If you have questions, please jot those down and they'll pass them up to us. Our next speaker is Bob Howarth. The title of his talk is The Greenhouse Gas Footprint of Shale Gas.
Thank you, Rob, and thank you to you and all of the organizers for pulling this event together. I think it's a very important event, and I'm very pleased that you invited me to participate. I want to quickly run through our work on what the greenhouse gas footprint of shale gas looks like. As I get started, let me acknowledge up there 2 co-authors, Renee Santoro of my department at Cornell University, and Tony Ingraffia, a civil engineer who did his PhD on hydraulic fracturing back in the 1970s and is the person we've relied on for our technical advice on this. What you're looking at is the summary figure of a paper we published back in April of this past year. Our paper was the first real comprehensive analysis, not only published in peer-reviewed literature, but published at all on the total greenhouse gas footprint of shale gas. It's proved to be extremely contentious. I sort of knew it would be contentious when we put it out. It was contentious well beyond what I imagined. And just to give you a a handle on that. Last month, Time magazine named Tony and I as 2 of the 50 runners-up for Person of the Year because of the newsworthiness of this paper. So it's contentious. I want to show you today what our conclusions are and then run through some of the work that's been done since then by others, and let me tell you what I think the status quo is. So to start with, what you're looking at here, we're using the global warming potential. I liked many aspects of Steve Hamburg's talk this morning. Steve emphasized that this is not the way to make a policy talk. We're doing it anyway. It's the way most science has been done on looking at greenhouse gas consequences of fossil fuels. We're following the protocol of the Intergovernmental Panel on Climate Change. I agree with Steve that better tools are needed. They're not there yet, so this is the best tool available to us at the time we put our paper together. What's the take-home message? We did a full life cycle analysis. We looked at 2 time frames, 20 years and 100 years, following this pulse of emission from an activity associated with shale gas development. The blue bars are the carbon dioxide emissions associated from burning a fossil fuel. And we're looking at shale gas with a low estimate for methane emissions, a high estimate, conventional natural gas with low and high estimates, coal from surface mines and from deep mines, and diesel oil. So indeed, you can see that there's less carbon dioxide per unit of energy, these are all normalized to energy, from shale gas or conventional gas than, say, coal or oil. However, we looked at the indirect carbon dioxide here too, that little red bar. I won't go into it all. It's extremely tedious work and really boring, and it's not very important. But the magenta bars there are the methane component of the greenhouse gas emissions, based on our best thought of what the emission rates are. I'll say more about that in a second. And at the 20-year time frame, you can see that even at our low estimate of shale gas emissions, the greenhouse gas footprint of shale gas is higher than that of any other fossil fuel, normalized again to the energy production. The 100-year, well, you know, at the high end, maybe it's worse than coal. At the low end, it's not. I want to stress the 20 years as I move ahead here a little bit in the talk. Let's see, what am I doing here? Okay, what are our methane emissions? A lot has been done since our paper. The paper came out only 8 months ago, and yet a huge amount of work has been done since then. I want to run through that quickly. So what I want to show you here are the methane emission numbers, normalized again per unit of energy as the fuel is burned. And this is as of the time our paper was published, our work and the only previous work. No one had looked at shale gas before. But when you look at conventional gas, there's a 2002 paper, a 2007 paper. There's actually a big range associated with this 2002 paper, far broader than our range, but that's what they call their best estimate. Their best estimate is about in the mean of ours. That's not entirely by accident. We relied heavily on their work in deriving our numbers. We also used a report from the General Accountability Office. We used new information from EPA that came out only November 2010. We used some unpublished industry sources. We think that there's a lot more methane. We say about 40% more methane on average from shale gas than conventional gas due to a large amount of venting that occurs of the gas at the time of flowback and hydraulic fracturing. Now, what's happened since? Since our paper came out, oops. Since our paper came out, there have been a huge number of other studies, both in peer-reviewed papers and non-peer-reviewed reports, and I'm showing them all to you here. Let me run through them quickly. First, the Environmental Protection Agency. Up until November of 2010, the Environmental Protection Agency was using emission numbers for the natural gas industry that dated from 1996. Those are the numbers that Yamarillo et al. Used. We thought at the time we put out our paper they must be too low. There's a lot of evidence for that. EPA agreed. So in November 2010, they started increasing their numbers. It's a work in progress, but as of May 2011, they put out these numbers for conventional gas and shale gas. They are saying there's 60% more methane emissions from shale gas than from conventional gas. Steve's talk is based on this number, I believe. Conventional gas. So if you take these numbers at face value, and this is contentious stuff, I will readily admit, then shale gas is far worse than conventional gas. The situation is worse than what Steve said. Hughes put out a report. He simply used our data. Zhang et al., which is the same group as Yamarillo, put out a paper. They have a lower estimate, and I won't say too much more about that. Holtman came out with a recent paper which has numbers very similar to the new EPA numbers, basically derived on those. Scone from the Department of Energy has numbers which are lower than the EPA numbers. That's for two reasons. One is that they're more optimistic about the total amount of gas produced per well, and all these are normalized to production. And secondly, they believe that the amount of emissions in distribution and storage systems is a lot less than EPA thinks. By the way, our high-end numbers are higher than EPA's because we think that perhaps there's a lot more leakage in storage and transmission and distribution than EPA thinks. And EPA, in fact, is reconsidering that at the moment. I don't know if they'll agree with us in the end or not. Scone et al. Numbers, too, though, say that there's 60% more methane emissions from shale gas than conventional gas. It's a new paper by Burnham that just came out last month. It says the opposite. It says there's less methane from shale gas than conventional gas. That's because they assume that this process called liquid unloading never occurs in shale gas wells. I believe that's wrong, but it's subject to debate. Their numbers are otherwise lower, in part because they made a calculation error, quite frankly. They should all be increased by 30% for that reason, but that would be a systematic number. And then Larry Cathels has a paper that was published last Friday that is largely a critique of our study. He says there's no difference between shale gas and conventional gas, and the numbers ought to be much lower than what we or anyone else says, but he actually doesn't document where he gets those numbers from. So this is the range. Obviously, I think our numbers are reasonable. That's why we put them out there, and I've seen nothing since publication that would make me change my mind on that. But there's nothing that's particularly right or wrong about any of these numbers. I think the range you see here reflects the range of uncertainty. And so, as we said last April, there's really a pressing need to get better data. Really pressing need. But our numbers are not outlandish, which some of you may have heard in the blogosphere. That's simply not true. Okay, time frame. Another aspect of the studies. How am I doing on time, Ron? Okay, thank you. Thank you. Time frame. As I say, we're using this global warming potential, a shot-in-time approach, not the continuous approach that Steve has argued for. There are a few other people who have used continuous approaches in the past for conventional gas. Hayhoe is one. Wigley's done it for shale gas. We chose this global warming potential because it's easier to do, quite frankly. But keep in mind that the science behind looking at the details of that is complicated and also evolving. So, for instance, most of these papers, they use a 100-year time frame. They use a global warming potential that's out of the IPCC 2007 report. That's only 4 or 5 years ago. Seems pretty recent. But the science has evolved. So Drew Shindell came out with a paper in Science in 2009, and he came out with a new paper last week, which give new global warming potentials that are much higher for methane. Why is that? Well, it's because of a new understanding of how methane interacts with other radiatively active substances and amplifies their effect over time. So our paper captures that, and we need to be careful that other analyses do. We looked at both the 20 and 100-year time period. Hughes did. Hayhoe used this continuous approach, as I say. Everyone else out here looked only at the 100-year time frame. And I don't think that's acceptable. 100 years is important, as Steve said, but so is the shorter time frame. And why? Well, let me invoke Jim Hansen in making my case. Hansen's actually written extensively on this, but this is a 2007 paper. And he actually makes the case that it's more important to control methane than it is carbon dioxide if you're serious about global warming. Not only because it's a stronger greenhouse gas, but because you'll see more immediate consequences, and if we ignore methane, we're in a lot of trouble, according to that study. Amplifying on that, the United Nations put out this report last August, and the Shindell paper that came out in Science last week amplifies on that and shows a figure that's very, very similar to this. So let me spend just a minute or so talking you through here. This is the temperature, average temperature of the Earth relative to the long-time mean from about a century or so ago. And it's gone up in time to 2011 there. And then we have 4 scenarios into the future. We have the IPCC reference scenario where we don't do much about greenhouse gas emissions. We have This red line where we take, starting immediately, aggressive action as a world to control carbon dioxide, and that helps, but there's a lag in how long it takes to have an effect, so the warming goes on for several decades anyway. Conversely, we have this blue line, which is the world ignores carbon dioxide but takes immediate steps to control methane and black carbon, and it has an immediate effect and helps keep us a lot cooler for quite a while. And then that line there is if we immediately control carbon dioxide, methane, and black carbon, which is clearly what we want to do. The yellow bar here is the point at which we start to have serious worries about undesirable tipping points in the climate system, such as, and this was the focus of the Hansen paper, warming of the permafrost and natural methane escaping to the atmosphere at unusual ways and causing a sort of runaway global warming. The point at which that's likely to happen is 1.8 degrees, and the yellow bar shows the danger zone for that happening. So we want to keep the planet below that, and the only way to keep the planet below that is if we control methane immediately. And if we do not control methane immediately, we run the risk that within the next 15 to 20 years, we will be at that sort of danger point for reaching these irreversible tipping points in the system. So the short-term view of the global warming potential for methane is real. And most of the available data, as poor as it is, including our study, shows that shale gas will result in more methane emissions than conventional gas. I said all of that. So, this is another summary of our paper. Nature republished it in September for the 20-year focus because of the importance of these tipping points. I still believe that's true, strongly. And this is my last slide. Let me just spend a couple of minutes. Do I have 2 minutes? I have permission for 2 minutes, so let me spend 2 minutes on it. This is my last slide. It's a summary of a paper we have, which I hope will be published next month. This is not based on our data, it's based entirely on EPA data, but it's my interpretation of EPA data. So let me tell you what we've done. We've used the very latest information on the national greenhouse gas emissions from EPA, not only what they updated last May, but some follow-up reports that they put out in July and September. And I checked with them last month, and these are the most recent data they have put out. So this shows first, for the entire United States, where the methane, as of the base year 2009, is coming from, and natural gas systems is the primary source of methane to the atmosphere from the United States. Animal agriculture is second, landfill, coal mining, et cetera, are less. They're important, but less. On the right, these pie charts show the entire greenhouse gas inventory for the United States, all gases, all sources of gases, so carbon dioxide is included in that, at two different time scales, using the most recent estimates of global warming potential from Shale, the 100-year and the 20-year. And using the EPA numbers, but Shale's latest global warming potential, you see that in the 100-year time frame, methane is making up 19% of the entire greenhouse gas inventory of the United States. And at the 20-year, methane is making up 44% of our entire greenhouse gas activity, all human activities in this country, with natural gas, again, being the major part of that. So clearly, we need to tackle methane emissions from natural gas. I think the best available evidence is that shale gas is worse than conventional gas. Most projections are that the primary use for shale gas will be to replace conventional gas in its current uses, heat being the number one of those, and that will have a measurable increase on the greenhouse gas footprint of the entire country. Thank you.
All right, thank you, Bob. Again, questions, or I'm sure we'll have lots. Give them to students coming up and down the aisles. For those of you who came in late, our third speaker, Art Berman from Labyrinth Consulting Service, is stuck en route between Anchorage and here, so he is late and won't make this session, may make later in the day. So we're going to jump to our fourth and last, well, our third and last speaker in this panel, and we've given folks a few extra minutes because of that. Kelvin Gregory is an assistant professor of civil and environmental engineering at Carnegie Mellon University. He works on such issues as the fate, transport, and toxicity of nanomaterials, as I mentioned in the original introduction. And he's going to be talking today about navigating water management challenges during hydraulic fracturing for shale gas production. And here's a pointer.
Okay, thank you very much. Well, we've heard a lot of very interesting and somewhat gloomy and doomy kind of scenarios for hydraulic fracturing and shale gas production in the United States, particularly from the perspective of global climate change and so forth. I'm going to be giving you a little bit different picture here, looking very much at water and the evolution of really novel technologies that are helping enable natural gas production from the Marcellus Shale. And I think the important take-home message here is that the problems associated with water management are very local. Even within one single county, they may be variable from site to site. And so there are going to be different solutions to the management of flowback water, and also the availability of makeup water that are going to be local solutions that are going to be motivated by the availability of resources and stressors with regard to the infrastructure that's available for managing the water and the economics, of course, as well. Before I get into the meat of what I'll be talking about today, I'd like to acknowledge my collaborators here. First and foremost, Professor Radoslav Vidic at the University of Pittsburgh. He and I have been working together on a variety of water issues associated with natural gas extraction for about four or 5 years now. Pete Miller at Range Resources, he's been a top-notch collaborator of ours. Rick Hammock at NETL, you'll be hearing from him tomorrow. He's one of our panelists. And then the students and postdocs who've been working on this project, Dr. Elise Barbeau, Arvin Miralai Mohan, and Adway Benwale. All right, so as we know, our shales, our gas-bearing shales are a very low permeability matrix from which we need to introduce engineered permeability in order to enable economic recovery for commercial volumes of gas. We've been producing gas from the deep subsurface for a long time, and even from shales through natural fissures, and there's old wells really puncturing the better part of Pennsylvania. But those gases are largely from natural occurring fractures, and so the economic recovery of shale gas has really been enabled by horizontal drilling and accompanied by hydraulic fracturing, as we've heard. Why horizontal drilling? Well, it really is greatly increasing the economics of this, but it also has a great environmental benefit as well. So this figure right here is really showing what you might have on a 500-acre site doing conventional vertical wells in these pink versus a system of horizontal wells. You have a single pad site. Greatly centralized operations, less land disturbance, and lower construction costs. So the environmental impacts are decreased, as well as improving the economics of it. So I'm not going to dwell on this slide. We are aware of what hydraulic fracturing is, but the important thing here, the important message is that we've got a fairly large amount of water that's being used initially, maybe 7 to 18 million liters of water mixed with sand and other chemicals that are used to protect the downwell infrastructure, as well as stimulate the well and maximize production volumes. About maybe 10 to 30% of that water is going to return as flowback water. When it returns to the surface, it's impounded. And over time, long periods of time on a well, you may see produced water happening over the entire lifetime. No one's really sure what the lifetime of the wells are going to be or how long produced water is going to be occurring. But the flowback period is going to be dependent on really the producer and the site itself. Produced water volumes, no one really knows how long the produced water phase is going to occur, but you might have 10 to maybe 20 or 30 days of flowback and a lifetime of produced water. Here's an overview of a hydraulic fracturing going on in southwestern PA. If we zoom in on this, you can see the impoundments that I'm referring to right here, as well as the pumper trucks and so forth. Here's the fresh water lines running in from off-site. The important thing here is really the chemistry and the water quality and water quantity of the flowback water. So over time, what we see is a great decrease in the amount of water that is being produced. Our produced volumes here, we've got about 1,500 meters cubed per day, all the way down here to a few barrels per day over time. Our total dissolved solids, though, are increasing very quickly here as we move from the high volume production to the low volume production. Obviously, the water that is flowing back here after 100 days has been in contact with the subsurface for a longer period of time. You've got higher concentrations of total dissolved solids. When you impound this water, you effectively integrate under this curve. So although you may see water that is as high as 200,000 milligrams per liter of total dissolved solids, or even north of that, 260,000, really, when you impound it, you integrate under this curve. So you wind up with a solution at the top, so maybe 100,000 milligrams per liter, or 60 to 100,000. These flowback water constituents, these are some broad bins here, calling these low, medium, and high. This is from a publication in Elements magazine from a few months ago. These are just some bins that we're sticking these numbers into, and just to give you an idea of what kind of concentrations that we see. So a fairly low concentration in flowback water, 60,000 milligrams per liter total dissolved solids. Of course, you've heard there's barium, strontium, bromide. These particular wells, we did not see any radioactivity in. But out here in the high concentrations, like I said, 260,000 milligrams per liter of total dissolved solids. So this is really what the management problem is really the high concentrations of salts that are in the water. And how do you dispose of those? How do you manage them? So these solutions to how you manage this really boils down to local infrastructure and well, it's all local here. So what we have is high volumes, high TDS, low discharge limits. Now, reinjection has been largely the technology that was used in developing the Barnett Shale. That's where a lot of the technology that came up to Pennsylvania originated. There's not a great opportunity to be doing this in Pennsylvania. There's about 50,000 wells in Texas. There are about 7 in Pennsylvania. There are more, of course, in Ohio and West Virginia, but we've got a high hauling cost associated with that. Dilution into POWTs, there's a few permitted, is ultimately not sustainable. You'd have to be diluting these things from 100,000 milligrams per liter down to 500 milligrams per liter. That requires very high volumes of water. It was never a very sustainable solution, but kind of a Band-Aid that was put on it at the very beginning of the development of the Marcellus. Ag reuse has been proposed, but you see salinity becoming toxic at 2,000 milligrams per liter of TDS, so it's not really a very viable technology. There's, of course, membrane technologies that are fairly effective. Of course, RO is best below 40,000 milligrams per liter, but again, this is also a very expensive process, and there's residuals you have to deal with. Thermal distillation is ideal for these briny solutions, 100,000 milligrams per liter and north of that. Very effective at producing crystal and brines and so forth. But again, these are residuals that you have to deal with, and it's a very expensive process. Freeze-thaw evaporation, not really, it's going to be more ideal when you get around Alaska, but in Pennsylvania, not a very good solution. I've heard proposals for artificial wetlands to deal with this water, but I mean, even mangroves begin to suffer at around 75,000 milligrams per liter of TDS. So, artificial wetlands for treatment of this water may not be all that effective. So there isn't a really great obvious solution for managing flowback water in Pennsylvania, but necessity, of course, is the mother of invention. And one of the principal technologies that has been evolving out of development of the Marcellus Shale in Pennsylvania is the reuse of flowback water for subsequent fracs. We heard about that mentioned earlier. So flowback water from the wellhead is then impounded, or essentially equalized, and you integrate under that curve in these impoundments. You may have a treatment process that happens prior to recycling. It's going to be precipitation to remove divalent cations, followed by settling. Then you mix your flowback water amendments. You may be diluting that water down, and then reusing the entirety of that flowback water for a subsequent hydraulic fracture. This technology really was developed developed on the Marcellus in around 2006 with the very first test wells, and you see that most of the large producers on the Marcellus are heading this direction. Now, the advantages to this are sort of obvious at the very here. We greatly reduce volumes of treatment and disposal costs, less fresh water withdrawals, lower risk to infrastructure, impacts associated with hauling, and more importantly, it's doable. And what I mean by doable is that there appears to not be too much of a detriment on production rates at the wellhead of gases. So this seems to be economically feasible from a gas production side, as well as from reducing the costs associated with treatment and hauling. And of course, those come with environmental risks as well. The challenges here are largely, these are, again, are local challenges, logistics and cost associated with transportation. Where is your next frac? Is it on the same well pad? Is it on a well pad that's in a close vicinity? Can you use a centralized impoundment, for example, in order to manage that water for multiple pad sites that are around that are clustered around a single impoundment? One of the big ones that may be emerging here is that smaller producers may not be able to utilize this. Smaller producers may not have a subsequent frac that is in the neighborhood that is going to be economically viable for them to either haul or have a very large impoundment in which to store this water and then subsequently use it for another frac. Again, we have larger impoundments, longer storage periods. So rather than just having that water impounded for a short period of time, it might be in there for weeks or months even, and this gives rise to aesthetics issues. These are microbial biogeochemical processes that are happening in the impoundments, largely sulfide being one of the key aesthetics issues with the impoundments. You've got grandmother putting the apple pie out on the window and an impoundment that's 1,000 yards away. We've got sulfide boiling off the impoundments. So managing, understanding the biogeochemistry in these impoundments over these longer periods of time is kind of a critical research issue. And then how do you develop management strategies for handling these impoundments that may be around for a fairly long period of time? There's potential economic risks associated with highly variable water quality, stability of frac chemicals and brine solutions. This is one of those sort of we don't really know kind of questions. We have no idea what the stability of these frac chemicals are in brine solutions. If you talked to people 4 years ago, they would have said, we need slick water, we have to frac with no more than 10,000 milligrams per liter of total dissolved solids. But now it's very conventional for fracs to be happening at 50,000, 60,000, even 100,000 milligrams per liter of total dissolved solids. And I've heard anecdotally, well, I shouldn't say anecdotally, there was kind of a joke said by one of the producers saying, we can frac with peanut butter now. So there are some challenges that are associated with this. Unknown water quality parameters for fracking, that's what I was kind of alluding to. We don't really know what the optimal water quality parameters are for hydraulic fracturing. What is that upper limit of total dissolved solids? It doesn't appear to be one right now because we keep adjusting it higher and higher and higher. Again, one of the important things here is the biogeochemistry of the impoundments and how long that water is going to be there. These impoundments, this is an impoundment in Washington County. Now we've got hydrocarbons there, of course the initial fracking fluid components, high total dissolved solids, naturally occurring radioactive materials in some cases, and of course we've got microorganisms there. Despite the industry's best attempts to kill bugs with glutaraldehyde, it doesn't work. The bugs come back, and they come back with reckless abandon and really take over these impoundments very quickly. But this, of course, gives rise to aesthetics issues associated with sulfide and fermentation, corrosion of infrastructure as a result of the microbiology in these impoundments. But also, perhaps, and this is going to be important for the ability to reuse water, that is the fate of metals. What is happening to the metals that are coming back in the flowback water, and in particular, naturally occurring radioactive materials? How's the microbiology affecting the impoundment geochemistry and the solubility of these metals? Over a period of time, do we see that the metals that norm is associated with the solids in the bottom of the impoundment, or is it still in the aqueous phase? That's going to be important to know for the reuse and some of the directions that we're taking at Carnegie Mellon. The other sort of key technology that I wanted to mention here with regard to new ideas for solving some of these water management issues in Pennsylvania, and that is the use of abandoned mine drainage as makeup water for hydraulic fracturing. So what I'm talking about here is essentially taking makeup water, flowback water and abandoned mine drainage water and creating a mixture for subsequent hydraulic fracturing, or even directly using AMD as a source of makeup water for hydraulic fracturing. some of the ongoing projects that we've been working on are trying to determine the chemistry of AMD and the flowback water blending. What is happening? We've got lots of sulfate that is in AMD. What's happening to barium, strontium, calcium, radium, things like that. Turns out the kinetics of this reaction is very fast. We form very insoluble precipitates very quickly. We want to understand the fate of radium during this blending and the microbiology and biogeochemistry of these impoundments in the water, when we're storing them on site. What's going to be happening to the AMD as it's stored? Unfortunately, we've got a lot of AMD around Pennsylvania. So here's a map of known AMD sites down here in the bottom. Here is a map of well sites. So these things are, unfortunately, we've got a lot of AMD, but fortunately they are co-located where a lot of wells are sited to be drilled or are currently being drilled. So you overlay these maps, and it is likely that there is going to be an AMD source that is readily available for use as a makeup water for your fracs. The advantages here are sort of obvious in that abandoned mine drainage, as some of you may know, is probably the largest pollution problem in the mid-Atlantic region as far as water is concerned. In Pennsylvania, we got about 4,500 miles of contaminated streams in Pennsylvania. Now, you probably can't see right here, but this is a creek that is running through the southwestern part of Pittsburgh right here. This is on Google Maps. It is bright orange. This is where the abandoned mine drainage from what the Gladden mine is meets this Chartier's Creek at Miller's Run, and this is really kind of one of the banes of the Pennsylvania DEP. There are challenges here to the ability to use this water, and probably the key one here is regulatory. My understanding is that if you use AMD water, and that is abandoned mine drainage water, not acid, not currently active mine water, but abandoned mine water, you use it, you own it. If you gain economic benefit from using that water, i.e. you frack with it, you now have to provide in perpetuity for the treatment of that water or the other kind of disposal of that water. So there's regulatory issues here is really the key, because the logistics and costs associated with transportation, those are going to be highly dependent on site by site, variable water quality and quantity. We see the mine pools filling up during heavy water times, the flow rates increase, we've got variability over an order of magnitude. And of course, potential downhole precipitation of these divalent cations when you mix with sulfate may give rise to decreased permeability in those wells. Got a couple publications out where we talk about some of these water management issues, and in the end, I'd like to thank our supporters right here, Range, and collaborators at University of Pittsburgh and NETL, and the support from National Energy Technology Lab. And I was just off in India in the Cambay Basin here, where they've got a fairly large shale gas discovery out, and not surprising, Cambay's got all sorts of oil out there, but there's I was over there talking about water management in water-stressed regions, which is going to emerge as probably a very critical issue sometime down the road as we start going into developing countries that don't have much water and extracting shale gas. Anyhow, thank you very much for your time.
Can you hear me? Yeah, there we go. Thank you. I'd like to ask the speakers to come up here, please, and sit at the table. We'll take questions from here. Again, to repeat myself, if you have a burning question, find a student or someone walking up and down the aisle and jot it on a note card. We'll try and make our way through as many as possible. We've left a lot of time for questions intentionally in this session, so we should be able to make it through quite a few. Okay, well, first, thank you all again. I'll have two questions. I'll start with one and I'll end with one. I guess if you had one scientific measurement that you could make, or what's the most pressing need for a scientific measurement that would be the most helpful for your work? And I guess a related question would be, what's the weakest part of your own analyses right now? So tell the audience what you would most likely to have, and maybe be a bit open about what you think the shortcomings of your own work is. Do you want to start, Bob?
Sure. And the answers to both your questions are the same. The methane emissions data that we're using are very poorly known. The quality of the data behind them are poor. The numbers I showed, I think, are about as good as you can do. I think the EPA numbers are
good as well. Our numbers overlap, but that doesn't mean they're right. The quality of the data behind all of that is poor. So I think what we need is a much better handle on what the emissions rates are. And there are two aspects to that. One is to, I think, get into the field and make some actual integrated measurements on what the flux rates are. That's never been done. All of the emission estimates are based on sort of an engineering understanding of how particular compressors or particular seals leak, or a little bit of observation of the venting that goes on after shale gas fracking. But for example, our shale gas, our number and that of all of the other papers where I pointed out that people say that the shale gas emissions are greater than conventional gas emissions, in all cases that's based on a handful of reported, poorly documented data. So getting better field measurements of that, much larger data set with better documentation is critical.
From my perspective, it's not, I don't think it's really a data issue for us, other than I think what we need is to understand what the limitations are as far as flowback water. What is the quality of water that is absolutely necessary in order for a hydraulic frac to take place? If we're going to reuse AMD, environmental engineers need to know to what level do we need to treat this water. If we're going to use AMD, we need to know, can it be used as is, as a source, just right as it's flowing into the stream, or do we need to do a treatment process in advance of this? And without knowing what kind of what level of treatment needs to take place, it's difficult to put cost numbers on it, and really cost is what is going to be driving all of this. And so I think it would be great to have numbers maybe from the industry that say this is what this is the kind of water quality that we need in order to be using a particular makeup water for hydraulic fracturing. It's clearly evolving. If you talk to people, as I alluded in the talk, it was 10,000 milligrams per liter 4 years ago, and it was just at 20,000, and these are documented in the literature even, and now we're up at 100,000, and maybe we can frack with peanut butter, but it would be good to know that we can.
So I think the issues that I would, in terms of a shortcoming, is maybe accessibility. When we're trying to evaluate water contamination, we go to homeowners, and we were pretty successful in Pennsylvania. The doors were open. We were able to get decent numbers of wells to sample for the water chemistry and quality. However, and I think one of the objectives of this workshop, hopefully, is to kind of destroy the gap between the industry and academia in terms of working together. And I think what we are lacking is the ability to work together with the industry to be able to bridge and to be able to sample and to collect water sample in a way that we want, not in a way that we enforce, because right now we can only collect sample, for example, from the wells that are located next to the shale gas well. But having the ability to sample the fracking fluid itself, the flowback as it goes, and to drill research boreholes in the vicinity of those shale gas well to make our study will be much more perfect and correct. Because we are having, from analytical point of view, we're having accessibility basically at Duke, for example, for a very large spectrum of geochemical and for inorganic, organic right now with the School of Engineering, and isotopic fingerprint that we are able to look and to evaluate the source of water in aquifer to tell where it's coming from. We have this capability. However, we do not have the capability to collect the water where we want to be. And that's the thing to be one of the issues that we are facing.
Okay. We'll work our way down the table, if you will, starting with Bob. But please feel free to chime in if you want to respond to one of the questions to a different person. Bob, we'll start with you. Here's a question from Caldwell Bailey. The question is, how much of the emissions differences in extraction of conventional and unconventional gas can reasonably be attributed to the newness of the horizontal drilling fracking process as opposed to the tried and true? conventional gas extraction process. Are improvements in technology and techniques taken into account in your study?
Yeah, it's a good question. The only difference in our numbers between the conventional gas and the shale gas is the venting immediately after hydraulic fracturing, a relatively short flowback period. That's also true in the EPA assessment, and it's true in the Holtman et al. Assessment, which is the other one I focused on in the brief presentation there. Other aspects of changes in technology are not reflected in our study. If any of the methane contamination of surface groundwaters that we've heard about is reaching the atmosphere, that's not included in our study. Can the initial venting be reduced? And absolutely it can, and industry is giving a lot of pushback saying we and EPA even more so have overestimated the amount of venting. Venting is the purposeful emission, could be flared and burned, in which case, has other pollution issues, but it's no longer methane, which is better from a climate change, or the gas can be captured and sold to market if you have pipelines on there. Technology exists to do that. The question is, how common are those various procedures? And the answer is we don't know, because there's not a reliable source of data. The moment EPA is assuming that 85% of that flowback gas is vented and 15% is flared or captured for market. And they're pushing for regulation that would require capture and sale to market if pipelines are in place and if it's possible to do it. That clearly would be a big help forward. EPA thinks you could reduce those initial emissions by 95% if you can get that to happen uniformly. I think that's a little overly optimistic, but 80% for sure I would find believable.
Okay. Here's one for you, Kelvin. It's comforting to me to know that there are people in the world whose handwriting as poor as mine. So if I get your question a little bit wrong, bear with me. Kelvin, what percentage of treatment costs what percentage of treatment costs compared to overall production costs does the flowback water treatment represent potentially? I'll let you look at it.
Good luck.
Passing the
Right,
question.
right, yeah. No, actually, yeah, that seems a bit, that's a great question. That is one of those questions that is very hard to get your head wrapped around, because the treatment processes that are necessary, so to speak, are going to be dependent on local conditions. What is the strength of the flowback water, and to what degree are you going to be treating it? If you're trying to turn this into drinking water, you're going to have very high costs. If you're just trying to remove some of the basic divalent cations from there and you're going to precipitate them with sulfate, it's fairly inexpensive. To tell you the truth, I can't give you a good number for what fraction it is, but ultimately this is really driven by the economics of it. With natural gas prices as low as they are right now, the feasibility of even using shale gas as a resource nationally has been called into question by a number of people in the oil and gas industry who study this. Is it even feasible at these low gas prices? So even I think the take-home message from that is that there's even small tweaks in what the cost is for treating water per barrel is going to overall have a fairly large impact on the economic feasibility of shale gas extraction.
Okay, thanks. Here's one from Therese Vick. The question is for Abner. Can the radioactivity be removed from the flowback and drill waste prior to disposal? And what happens to the hot pipes after their useful life is over?
So yes, radium, which is the major radionuclide element, can be removed. It's actually pretty simple process. However, by second law of thermodynamics, you still end up with the residual, and the residual will become even more radioactive. So when we're talking about natural occurring radioactivity and the removal, so the actual treatment by softener could be very simple and cheap process to remove radium. However, you end up with some higher concentration, lower volume of residual that you need to either to put it in a specific landfill that should be protected and should be allocated for disposal of radioactive material. So the problem of disposal, it's kind of more complex than just removal and reducing the volume. Now, that's true. If you don't treat radium, you would end up with co-precipitation of radium into pipes, and it could be a long-term source for radon emission, which is the daughter isotope that's coming from radium into the pipes and the water that's flowing through the system. So there is a danger if somehow high enriched brine, radium-enriched brine or water flowing through a pipe, and we see this in Texas actually right now in some areas that can cause long-term water issues with radon and some radium residual in the water.
Want to add anything, Kelvin?
Well, one of the, I guess, one of the important things to recognize, the radium is in such low concentrations that it can't precipitate with a simple sulfate precipitation by itself. It co-precipitates along with barium and strontium. So you need to have barium and strontium present in order to remove the sulfate, or I'm sorry, in order to remove the radium. But you do get a nearly complete removal of uranium as a co-precipitate along with barium and strontium when you're doing sulfate precipitations. The ability to accept the radioactivity at a landfill, for example, I think is an important issue. I know that all the producers that I speak with, they have not had problems disposing of it even at municipal landfills. Even if they have to test it for the radioactivity, and they have not had issues with it. But that's not to say that every produced water is going to be disposable at a municipal landfill. There may be stuff that's got high enough radioactivity in it that it needs to be taken to a licensed radioactivity landfill, which would greatly increase the costs of disposal.
Perhaps one comment. I mean, we are focusing on the Marcellus brine or produced water, which are enriched in radium, but that may not be the case for other basins across the country. So we should be careful. I mean, obviously the Marcellus brine are very highly in natural occurring radioactivity, but that's the case may not be valid for other basins. So this problem may not be, for North Carolina, for example, in the future, may not be an issue.
Okay, one for Bob. This is from Greg Staple. Bob, please comment on Professor Larry Catley's rebuttal paper, where you agree, where you disagree. How should data gaps on methane emissions from shale gas production be closed?
Thank you. This is a frustrating question for me. For those of you who don't know, Professor Larry Catley is a colleague of mine at Cornell, and he's published a paper. It's actually prematurely published by accident by the publisher, but it came out last Friday. It's a fairly long critique of our paper, and it lists a whole bunch of ways that he thinks we're wrong or things that we got wrong. We have a invited rebuttal from the editor, the publisher, which is some of what I showed you today, that I hope will be published within the next week to 3 to 4 weeks, something like that. They're supposed to be co-published. They weren't due to a mess up by the publisher. Where do I agree and disagree? Well, I showed you Professor Catley's numbers for methane emissions. They are lower than any other estimates that anyone has come up with. He didn't provide any documentation as to where he got those numbers from. He just says that they ought to be like that. He said that the shale gas emissions are the same as conventional gas. We disagree with that. We're in good company when we disagree. Most other studies have also disagreed with him on that. He says it's inappropriate to use any time scale other than the 100-year analysis, and I disagree with that. I think that both the short and long time scales are critical, but particularly the short time scale because of this urgent need to address possible tipping points in the global climate system. Those would be the prime areas in which we disagree. He goes into a lot more detail about how the initial venting we estimate can't be right. He says it wouldn't happen because it's unsafe. Well, it does happen. EPA thinks most of the time. I've seen it personally. There's plenty of documentation that it happens. He says that industry wouldn't allow it to happen because they would turn a profit by selling the gas back to market. EPA's done the calculation, and generally that's true. If you're a non-exploratory well, non-exploratory area, and you already have pipelines, gathering pipelines in place, so you can put green completion technology into place and take it to market. It is indeed cost effective, but EPA estimates an economic return of about 5, 6, 7%, as opposed to the industry norm of over 30%. So clearly industry's not doing that. He also says it's illegal in most states and therefore it doesn't happen. That's simply not true. It's a misinterpretation of law. So we disagree on almost all points, and it's frustrating because we sit in the same part of the world on the same small campus.
Okay, Kelvin, this is a question from Wendy Graber here at Duke. How promising is the use of acid mine drainage as a fracturing fluid replacement? What percentage could it replace, for instance?
Yeah, that's a very good question. So I think let me give you the answer just straight. Hydraulic fracturing is not going to solve the AMD problem in Pennsylvania. Pennsylvania's abandoned mine drainage problem is galactic compared to what the potential benefits are from using AMD as a makeup water. But there are going to be sites, specific localities where removing that source of contaminant from the waterways by directing AMD towards hydraulic fracturing are going to have benefits on individual communities and not necessarily statewide. You're going to be handling the AMD problem. We're talking about fractions of a percent of the AMD water, and the AMD water is also a perpetual source. It rains, the mine pools fill up, and we get more AMD spilling into the waterways. So it's, I think it's going to be a great solution for individual municipalities where AMD is a problem, and there are fracs that are going to be available. The problem from the regulatory perspective is the real one that needs to be dealt with, in that once a company uses this for a benefit, they are now responsible in the future for managing that AMD source. And there aren't many companies out there that are going to say, I'm going to take on this highly variable, unknown cost onto our books in terms of liability. So there could be maybe from a policy incentives, tax incentives that could be set up to enable the long-term treatment of these AMD sources and really do rejuvenate those streams that are impacted by AMD.
Okay, here's an unlabeled question. Abner, could increased methane levels in water wells serve as an indicator of other potential contaminants, such as organics, benzene, toluene, xylene, or other chemicals used in hydraulic fracturing?
Well, the simple answer, we don't know. So far, we haven't seen arrival of dissolved constituents into drinking water wells. What we see methane, and we have some measurements of organics. In those high methane wells, we have not found any significant or any tracer of those organics, like volatiles, for example, in those wells. So until now, the data, again, and we take it with caution because the limited data that we have so far showing that we see migration of stray gas to the drinking water wells, but we haven't seen arrival of dissolved constituent. It could be much more, the dynamics could be different, could be the time of arrival could be different. Could be that it's only flowing through a free gas, and therefore only volatile organics could be potentially be arriving to the wells. And it's also, there's issues of the reactivity of those constituents in the aquifer system before the arrival. Many of those organics are highly reactive. They will be absorbed, retained into the aquifer solids before arriving into the screen in which the shallow wells are located. So, but the truth, we don't know. That's the real answer.
Okay. Bob, one for you. Your research indicates shale gas has a larger climate impact than other energy sources, but were leakage to be addressed through best practices, how would this change the balance in your view?
That's an excellent question, and of course it's central to the whole issue. I already spoke a little bit here in response to the earlier question about what could be done to reduce that initial venting, and a lot could be done, but it's going to require regulation because the economics clearly have not driven industry to do it. But that initial venting could be reduced a great deal. I would like to see things go further than what the EPA's proposed and require them to put in gathering pipelines as well, but that's a small detail. The other aspects of the emissions are equally uncertain, but they include things like routine leakage at the well site, both the conventional wells and shale gas wells over the life of the well. Small leaks happen. That's not particularly well known. Those are going to be hard to tighten up, probably, although we don't entirely know. There's this process called liquid unloading that I referred to, where over the course of a well, liquid accumulates in the well and interferes with gas flow, so you have to get the water out of there. Traditionally, there's a lot of venting associated with that. Industry could try to capture that, but exactly how well they can do that is subject to debate and is not known. One of the biggest unknowns, the reason our low-end emission numbers are lower than EPA's at this point, and substantially so in some cases. Our high-end numbers are substantially higher and higher than anyone else's. And the reason for that is that we think there could be, I'm not sure, but that's why it's a high-end estimate, could be a lot more leakage associated with distribution systems and storage systems than EPA has been assuming. And EPA is still using decades-old data for their analysis in that. Nathan Phillips is in the audience here. He's working on that question in an urban setting. I think that's a real key thing. If we're right, and there's a lot of leakage in these distribution systems and storage systems, that, it's not that it's not fixable, but it requires taking century-old or half-century-old distribution systems out of cities and completely replumbing cities. And I don't think that makes any sense if we're talking about a couple of decade transitions to some other energy future. So again, we need to know how much of the leakage is associated with that in order to really know how this problem could be solved. But if we're wrong on our high-end estimates and those distribution systems are tighter than I think they probably are, and you were to get the industry to respond to strong regulation on the liquid unloading and the initial venting and things like that, then I think you possibly could take the methane emissions down to the point where it's an acceptable process. I doubt it at the moment. And in fact, we don't know, no one knows because the numbers are too uncertain.
Okay, thanks. Bob's talked a lot about issues of the lifetime of a well. Here's a question about well lifetimes in a different context for you, Kelvin. How many fracs will take place over the life of a well, and how will this affect flowback and subsequent impoundment for reuse?
That's another one of those questions that nobody really knows the answer to, or at least no one's going to be talking about it. Looking at, the question is getting at what the well depletion rates are going to be. How long is a well going to be productive economically, and will hydraulic fracturing or a refrac of an individual well, is that actually going to be stimulating higher production rates? I think most people would agree that yes, a refrac will stimulate will stimulate those higher production volumes, but no one really talks very much about what the depletion rates are because it's kind of it would potentially give competitors information about a particular region. I guess the answer here, unfortunately, again, is we really don't know to what degree refracking is going to be done on the Marcellus, but we're still pretty young and early into this. But as the age of these wells starts getting out there, at 5 and 10 years, we may see refracs becoming part of the well stimulation technology on the Marcellus.
Okay. Well, there's a lot of interest locally here in North Carolina because, as most of you know, our legislature is considering legalizing horizontal drilling and hydraulic fracturing. So here's a North Carolina question for you, Avner. This comes from Bob Elias. Let's see. Actually, this is. Let me switch to a different one. I'll hold that for a second. That's Kelvin's. The Marcellus gas formation is much deeper than ours in North Carolina. Here, the aquifer would be much closer to the fracking zone than in the case of the Marcellus. Please comment on how a shallow gas play might differ from the Marcellus. This comes from Chuck Sathram. For you.
So, I mean, the real issues is that when we published our paper in May, this was the first peer review publication that addressed the issues of affect water quality with shale gas drilling. And we are really in the first early stages of understanding and evaluation what's happened to the groundwater system as a result of drilling and fracturing well. And anyone who can give an answer for that basically can argue that he or she would understand what's happened in Marcellus, and I would be much more cautious. We see evidences, and we have more now that's going to be published in the next few months, that indeed the stray gas that we found in the shallow wells are coming from deep from the Marcellus. What are the mechanisms? We think we have some ideas about the mechanism of the flow of the gas, of the methane to the wells. If indeed the same replicate or the same mechanism would happen here in North Carolina, we would expect to see stray gas effect as well. Just because of the area that we are talking about is highly fractured. So there's some similarities between the geology on the target areas here in North Carolina, and if you compare it to the Marcellus Basin in northeastern Pennsylvania, which is a very highly fractured system, which made possible the connectivity between open casing areas in the well into the natural fracture system. But we really don't know. So I think we need a lot of science and a lot of research to really understand the mechanism of this flow before we can give a sensible and kind of assurance answer for this question.
Okay. Bob, this is a question that comes from Jeff. I believe it says Tucson. Are there economical technologies or management measures that can significantly reduce levels of methane emissions you've identified?
Yes, and again, I've spoken to those a little bit. For this venting that occurs right after hydraulic fracturing, the technology to capture that exists. It is used to some extent. You need pipelines in place to send the thing to market. To reiterate, the EPA says it actually is cost effective, but it's a very, very small economic return and appears to be too small of an economic return to encourage industry to be doing it widely. Depends also on the production of the well and the pressure of the well. There's another study by British Petroleum that's far more pessimistic about it in an economic sense. They put the break-even point on that technology at a gas price of around $6.50 per 1,000 cubic feet, I believe is the number, something like that. And of course, gas is around $4 per 1,000 cubic feet right now. EPA puts the break-even price at around $3.95 for context. So that technology is there. Some of the other technologies, you can use different sorts of seals in your compressors. That helps with some of the routine leakage. Storage systems often purposely vent gas because that allows you to more safely maintain pressure in the systems with thinner shell storage systems. So yeah, you can go to much heavier systems. That's pretty expensive. That's why they vent gas from these systems. And a fair amount, as I say, I think, though it's unknown, but a potentially large amount of the leakage is in the distribution systems. And let me give you a case in point. We were talking to the city of Philadelphia. They came up with an estimate at one point about 3% of the gas that went into the city, and then they backed off and said, no, they think it's about 1% or so, which, by the way, is still far higher than anything we or anyone else have estimated in our studies to date. But I think it's probably characteristic of the northeastern cities that it's a cast iron distribution system of pipes that was laid down around 85 years ago. The pipes are not welded together. They're stuck end to end with seals which were never renewed. So it is likely that those things leak. And the cost effectiveness of putting in all new distribution systems in an urban setting is very high.
Okay. Here's the question from Bill Elias. For you, Kelvin, how much natural gas mixes in with flowback water, and to what extent does that affect reusing flowback water for additional fracturing, or does it?
Natural gas.
Can I answer that?
You know,
issue?
I was going to say, I think one of you is going to have a better answer to that than
We've
I
actually
may
been
have.
looking at that, which you probably have. Because we wanted to get at that. When we worked on the first draft of our paper, going back more than a year ago, a year and a half or so ago now, when we were trying to figure out how much methane is released at the time of fracturing, we ran through the calculation of how much gas that would be, and assuming it's all vented, and it turns out to be a pretty trivial amount of gas. It's so small that we didn't even include it in our final report. So that my issue with the venting is sort of a free flow of gas after enough of the liquid gets out of the way that the gas is flowing, but there's still too much liquid underway for the gas well to be put into production. That's when most of the flow comes through. And the amount of gas that's really in that flowback water is small. It's probably pretty rapidly consumed by the bacteria that are everywhere.
And I guess with those numbers in mind, or not numbers, but with those relative quantities in mind, it's probably not going to be impacting the ability to reuse flowback water for hydraulic fracturing.
Okay. Abner, question from the USGS. Do you have any proof that the methane you found is a shale gas and not other thermogenic gas from the area? And was it caused by hydrofracking or simply drilling? And I interpret that to mean casing and production issues.
Right. That's kind of a question that came back to us pretty often. The evidence for the source of the methane is by the isotopic composition of carbon, delta C13, and hydrogen in the methane, which is looks like very similar to what we see in the Marcellus methane at that very area, like for example in the Dimick area. So in the paper that we published, we used the bulk isotopic fingerprint of delta C13 in methane. In more advanced study that we're doing now, we're looking for other hydrocarbon fingerprint which are confirming our earlier observation. So the answers we're using, whereas shallower and other sources of gas would have a different, much more mixed isotopic fingerprint. For example, we went to and this was published also in one of our responding proceeding of National Academy of Science. We went to a spring, a natural spring, salt spring, where the Native Americans 500 years ago used methane in the area. So this is a source of methane that it's naturally occurring. It has isotopic composition of one would expect to have thermogenic, and it does, but this thermogenic isotopic different is very different from what we see in the Marcellus. So for us, this kind of perhaps anecdotal, but it's demonstrate that there is natural occurring and thermogenic source of methane in shallow groundwater resources in northeastern Pennsylvania, but they are mixed between geothermal, thermogenic, and biogenic, and they are very and they are still different from a pure Marcellus methane. So, and the more data we are now generating, confirming those observations.
Bob, this is a question from Rob Steele at the Electric Power Research Institute. Please explain and define the differences of conventional gas and shale gas. Is it the chemical composition or handling issues, other differences?
From my perspective, the gas is gas. It's methane, and the only real difference is how it's obtained, not how it's used. So the only difference in our estimates, again, are the amount of venting of the gas that we think occurs at the time of flowback following hydraulic fracturing, that period of a few weeks to a month or something like that. Beyond that, gas is gas. And so a lot of the criticisms I'm laying on gas are all natural gas. But shale gas is worse if indeed our estimates or EPA's or Hultman's are correct in terms of how much gas is vented at the start.
Okay. There's been a lot written lately about water and using other things besides water for hydraulic fracturing. Peanut butter was a new one for me, but I'm going to use that in class. For you, Kelvin, here's a question from Janice Hencherick. Other than being cheaper than propane gel, why use water to frack when gas output is greater in gel fracked wells?
Well, so this is one of those technologies that are frequently being talked about right now, getting away from using water, particularly in water-stressed areas, and going to liquid propane fracs, and I've heard nitrogen fracs and CO2 fracs and all sorts of stuff. Economically, water works well. Those aren't entirely new technologies. They've been thought about for a while. Water works out economically from an environmental standpoint. If you're using, liquid propane, for example, you would not be pulling back a lot of radionuclides from the subsurface, and you wouldn't be having a lot of these dissolved metals problems that we have. I think some of the problems would arise, I think, in handling these frac fluids. But also, I think it would be tough from a homeland security standpoint to have 7 million gallons of propane in a tank next to some site. I think there would be some questions raised about the safety of those kinds of. But there's technologies other than using LPG that are out there, and I think they should be explored. And I think that's kind of a limitation right now. I think there needs to be some fracs done with these other frac fluids.
Okay. Here's one from NC State University, Abner. Could you address short-term impacts of produced waters from spills and illegal dumping? Are there fish kills and contamination of surface water supplies?
There were, obviously, if you heard in the media, there were several spills in Pennsylvania associated with drilling and fracking. And if you look at the numbers of trucks that involved in the fracking operation, you would say it's inevitable not to have spills and that level. But I haven't seen documented and a systematic analysis of what's happened to surface water and groundwater associated with spill site. So again, I think there is a lack of information with respect. We know about it's happening all the time, occasionally, but I haven't seen systematic studies that looking at the impact or the long-term impact of those spills. We have our own measurements. We did some studies of spill in some ponds in Pennsylvania, and we can see that what Kelvin mentioned, and what we measure in produced water, high salinity, high level of barium, high level of natural occurring radioactivity, that would be associated again with the spill water or the pond in which the spill water being contaminated. So, but there hasn't been, that I'm aware, a systematic monitoring of the quality of those sites.
Okay. Time just for a few more questions. Let's see. Kelvin, here's a quick one for you. This is from Flip Froelich. Drillers hate salt because steel pipes hate chloride and sulfide. Are any of the companies willing to try using Flowback as their primary fracking fluid?
Absolutely. It's going on right now. The majority of the big producers right now in Pennsylvania are heading in that direction. I think the resistance to it early on was that it was hard to find a company that was willing to take on that risk. The technology as it moved out of the Barnett Shale was, hey, you use a slick water, start off with tap, make your additions, and you've got a very well-defined source water, and that's going to optimize your wellhead production rates. However, there's been, Range Resources is one of those companies that really stuck their neck out there and tried one of these fracs and really pioneered that technology of using reuse of flowback water. And with them taking on that risk and getting those questions answered, others are now following suit, and you see some of the big producers going that direction. The limit is really with regard to the smaller producers. They may not have a subsequent frac that's going to be in the vicinity to make reuse economically viable for them. And I think what would be great is, in order to solve that kind of a problem and get reuse available to all the producers, is to have something like some kind of a produced water bank. I know that kind of flies in the face of regulations, because when you produce that water to the surface, you own it, and it might be difficult to get around. How could you enable another producer to be using your water? So if you've got water and another company's got has a lease adjacent to where you've got an impoundment, enable them to use that water. I think that kind of a water bank to allow small producers would be a great way of getting around that limitation of the ability to use fracking for every recycling for all of the producers.
Okay, one general question for any of you. This is from Elaine Chioso. Is fracking only a profitable industry because of lack of environmental regulation? Would fracking no longer be viable if new regulations are put in place to protect ground and surface waters or to reduce methane emissions? We should note that as you know, natural gas prices are quite low today compared to historic levels. So that's a very relevant question.
Let me take a crack at that. To begin with, I wish Art Berman were here because he could speak to this better than I, but it's questionable whether it's a profitable business at the moment. And for context, I was at the European Union in Brussels back in October. There's a workshop on shale gas in Europe, and the head of the International Energy Agency was there. He gave their latest information. The International Energy Agency says that the break-even point at which the natural gas industry would turn a profit on shale gas using current technologies in the Marcellus Shale is $6.17 per 1,000 cubic feet. And again, the current price is around $4. So if that's true, then they're not making money at the moment. And I think there's some evidence for that. You've seen a big shift in industry over the last year towards shale oil. Instead of shale gas, there's a much higher profit return in shale oil. Keep in mind that when the big push on the Marcellus in the northeast, the gas area started, the price of gas was far higher than it is at the moment. 3 years ago, it was over $8 per 1,000 cubic feet, which would have turned a profit. So whether or not that's really true is subject to debate. Art Berman says the break-even point's even higher. Chesapeake Gas says it's lower, so there's debate about that. But it's at least reasonable to think that it's not as profitable as industry would like it to be. And so each time you put an additional cost on, there will be resistance from industry. And exactly how much the various environmental safeguards will cost, I don't think has been well priced out yet.
Okay, last question, moderator's prerogative. 30 seconds for each of you, if you would. What technological advance or best practice would most help shale gas extraction in your view from an environmental standpoint, economic standpoint, whatever?
You want me to go first?
If you're ready.
Well, let me answer a different question. Should we be proceeding at all with shale gas at the moment? And I'm on record, Tony Ingraffi and I published a commentary in Nature last September saying, no, the technology's too new, the science is too new. Your Duke study just came out in May. Our greenhouse gas paper just came out in April. Science is moving, it's highly uncertain, and I think we ought to go very slowly on this until we better understand both how to do it better and what the consequences are. And meanwhile, I think we ought to have a moratorium.
Kelvin?
My interests are largely on the water side of things, and I think what is missing is, at least especially from the public perception standpoint, is there's not really a third-party, peer-reviewed kind of understanding of hydraulic fracturing, the management of water, the management of gases. There's a lot of internal memos, I'm sure, floating around out there in the industry, and they may have the best handle on management and best management practices, but they're not out there for the public to see, and they're certainly not out there for academics to review. And I think what we need is to have these kinds of third-party peer-reviewed studies so that we can move forward with the kinds of policies and regulations that are going to enable natural gas extraction while also greatly minimizing, if not eliminating, any potential detrimental impacts to our other natural resources.
I would agree that indeed science is much needed here, and we are basically facing a lack of science and lack of, I would say again, the integration and working together with the industry. The fact that there are some walls and inability of the academia to work with industry, I think that's one of the reasons that we have so many few studies in the peer-reviewed journal that have addressed this issue. So again, one of the objectives of this workshop is to try to break those walls and to try to understand the science and the policy that need to be addressed. And I think at that point, I would be more cautious. I think we really, even looking at the modeling of potential methane flow and release to the atmosphere, it's based on modeling. So we have to be cautious of that because we don't really know, haven't been really measured. Only few measured in groundwater contamination, like in our study. So again, take it in a proportion. And I think we are not ready yet to make a conclusive decision where we are. And that would be my cautious reply to that.
Okay. Well, first of all, thank you for giving us your morning and for your great questions. I'd like to remind people we'll be back here at 1:30 for the next session, which is titled The Legal and Socioeconomic Setting. So we'll look at people more right after lunch. I'd like to thank our speakers and have a good lunch.